Hello, this is Mrs. Ward, and this is going to be a video going over section 4.6, related rates, which happens to be one of my favorite sections. And the reason why it's one of my favorite sections is this where you can see where math is actually used out in the real world. We're going to find related rates, and then we're going to use these related rates to solve real life problems. And this section is entirely word problems, just so you know. So related rates allow you to find the rates of change of two or more variables that are changing with respect to time. So up until this point, when we did the implicit differentiation in the last section, we did our change in y with respect to x, so we did the dy over dx. Well, these ones are all going to be the change in whatever variable with respect to time. So our denominator of our dy is going to be dt. So we're always going to find how things are changing in respect to time. So when I think about this, I think about, like, let's suppose I had this cone, and I had water in this cone. So at a certain point, if I have water in this cone, this water is at a certain height. I'm just going to call that h. And now I'm starting to let the water flow out. And as the water flows out, it should make sense to you that the height of the water is also going to go down. As the water drains out, the height of the water goes down. That's not the only thing that's changing. The volume of the water is going to change as it drains out. I'm going to have less and less water in my cone, so I'm going to have less and less volume. And the other thing that's changing is when I talk about the radius of the top of the water, at the top it's going to be here, and then if I'm looking down here, the radius is going to be smaller. So three things are changing when I'm draining the water. My height of the water is changing, the volume of the water is changing, and the radius of the top of the water is also changing. And those all are happening in respect to time. In other words, how long the cone is draining the water out. So first of all, in order to do a problem like this, we have to first know the formula. So to find the volume of cone, that's going to be 1/3 pi r squared h. And just to remind you that I have three variables. I have the v, that stands for volume, r that stands for radius, and the h that stands for height. Remember, the 1/3 and pi are constants. They're numbers. So when I go to take the derivative, those are just going to come along for the ride, and I'm not going to do anything with them. Now, to take the derivative of volume, that's just going to be the change in volume with respect to time. Because there's no coefficient, so it's understood to be 1, so I'm just going to write dv dt. When I go to do the derivative of r and the derivative of h, I'm multiplying these two. So I'm going to have to remember to do the product rule while I'm doing this. So the first one, I'm going to take the derivative of, let's do the derivative of h first. So the derivative of h is just 1. So this will be 1/3 pi r squared. That r squared isn't going to change. And the derivative of h is 1. And then I'm going to write dh dt to show that I took the derivative of h in respect to time. Then I'm going to add, remember this is a product rule, the 1/3 pi is not going to change. Now I'm going to take the derivative of r squared, which will be 2r, then the change in r with respect to time, and then I still have that h there. So this is me taking the derivative of h, this is me taking the derivative of r. I'm going to rewrite that so it doesn't look so clunky. And then I'm going to take the 2 times the 1/3 and write 2/3 pi, and then do r times h, and then the dr dt. Because I'm multiplying it, it doesn't matter the order that I write this in. So that would be me taking the derivative of the volume function. So when you go to do these, what you're going to do is you're going to identify any given quantities, those that are being, and then you're going to figure out which ones you're trying to find and when. Because remember, everything is changing with respect to time, so I need to know when I want to have this happen. I find making a sketch very helpful in labeling quantities. Write an equation involving variables whose rates of change either are given or are to be determined. Use the chain rule implicitly differentiate both sides of the equation with respect to the time. After completing step 3, substitute in the resulting equation all known values for the variables and their rates of change. then solve for the required rate of change. This is very important that you do the derivative first, then substitute in what you know. So let's do what I like to call big. So my equation is y is equal to 2 times x squared minus 3x. And I want to find, for A, I want to find the change in y with respect to time when x is equal to 3. And they're telling me that dx dt is equal to 2. So the first thing I'm going to do is I'm going to take the derivative of this with respect to time. So I'm going to do dy, the derivative of y is just going to be 1. So I'm going to write dy dt is equal to, and you know, I would probably make this 2x squared minus 6x so I don't make any mistakes. And then when I'm going to take the derivative of 2x squared, I'm going to make that 4x minus 6. And then I'm going to put this in parentheses because I should really write dx dt by both of them. Because here when I took the derivative of 2x squared, it's 4x dx dt. When I took the derivative of negative 6x, it's negative 6 dx dt. So I'm going to put that in parentheses and just write that once. They want me to find dy dt when x is equal to 3, and they're telling me that dx dt is 2. So I'm looking for dy dt. They're telling me that x is equal to 3. And they're telling me the change in x with respect to time is 2. So this dx dt is 2. So I'm going to say dy dt is equal to, this is 12 minus 6, so that's 6 times 2. And I'm going to get 12. And I don't have units, so I'm just going to say that my change in y with respect to time is 12. That was part A. Part B wants me to find dx dt when x is equal to 1. So I'm still using the same derivative. And now they're telling me that I'm looking for dx dt. And then they're telling me when x is equal to 1. And they're telling me that dy dt is equal to 5. So I'm going to put 5 in for that dy dt. So I'm going to have 5 is equal to, this is 4 minus 6, that's negative 2. Dx dt, divide both sides by negative 2, and I'm going to have 5 over negative 2, or negative 5 halves. That's equal to my dx dt. And that's it. Not too bad, right? Now let's get into like a problem. The radius of a circle is increasing at the rate of 1 foot per second. Find the rate of change of the area with the area is equal to 4 feet. This is and b when the radius is equal to 10 feet. So the first thing I need to know is I need to find the area of a circle. So the formula for an area circle is area is equal to pi r squared. So now I'm going to take the derivative with respect to time. So dA over dt is equal to pi times 2r dr dt. I'm going to clean that up a little bit. dA dt is equal to 2 pi r dr dt. So that's the formula that I'm going to use. For part A, it wants me to find, it tells me the radius of a circle is increasing at 1 foot per second. So the change in the radius with respect to time is going to be 1 foot, or 1. And now A wants me to find this when R is equal to 4. So those are what I'm going to substitute in, and I'm looking for the change in area. So dA dt, that's what I'm looking for, is equal to 2 pi. My radius is 4, and my dr dt is 1. And when I do all that, I change in area with respect to time. It's going to be 8 pi, and it's area, so it's going to be feet squared per second. And I'm going with second because that's the feet per second is my rate of change. So that's part A. To do part B, I am going to take B is going to be the same thing except now it's 10 feet per second. 10 feet when the radius is 10. So I'm going to change an area with respect to time is equal to 2 pi and then 10 times 1. So that is going to be 20 pi, that's 1, 20 pi feet per second. And that's it. And let's try number 3. Of the distance between the origin and the moving point of the graph when y is equal to x squared plus 1 if dx dt is equal to 2 centimeters per second. So they're giving me, I guess I should get in the habit of writing my given. My given is my dx dt is equal to 2 centimeters per second. And they're also giving me the equation y is equal to x squared plus 1. So that's what they're giving me. They want me to find my distance, the rate of change in my distance. So I'm going to say they want to find the d for distance with respect to time. And then, so what I have to do is I have to find the distance. So if I have this point, and I want to find it on this line in x plus 1, so it's going to look something like this. So I want to find the distance between these 2 points, what's happening. So I have to do the distance formula. And the distance formula, remember, is the square root of the difference of the x's squared plus the difference of the y's squared. So let's make x1, x2, 0, 0, and then the other two, so I'm just going to find the x and the y. So I'm going to take the square root of x minus 0 squared plus y minus 0 squared. So I'm going to say my distance is the square root of x squared plus y squared. That's my distance formula. And then I am going to put it in, so give me a second. So my x squared is going to stay x squared. And then they tell me that y squared is equal to x squared plus 1. So I'm going to go x squared plus 1, but I'm squaring that because y is squared, so I have to square that. So I'm going to say this is going to be x squared. Now when I square this, if you want to do it opposite side, it's x squared plus 1 times x squared plus 1. Please don't forget the middle term, I'm begging you. X to the fourth plus 2x squared plus 1. So when I combine my like terms, I'm going to have x to the fourth plus 3x squared plus 1. And do we agree that I can rewrite this as x to the fourth plus 3x squared plus 1? This whole parenthesis raised to 1/2. Because now when I go to take the derivative of the distance, I'm going to have to use the chain rule. That's Mrs. Ward. So here I go. I'm going to do, if I want to do that whole u thing, here we go. My u is going to be x to the fourth plus 3x squared plus 1. So the derivative of u is 4x to the third plus 6x. The derivative of that one is 0. And then the derivative of something raised to 1/2. So let's say, I don't know what I would call it, let's say something raised to 1/2, and the derivative of that would be 1/2 u to the negative 1/2 times the derivative of u. So let's sort of incorporate all that. So we take the derivative of d, that would be the change in d, the distance with respect to time, is equal to, using this, I'm going to have 1/2 and x to the fourth plus 3x squared plus 1 and negative 1/2 times the derivative of u, which is 4x to the third plus 6x. Now when I multiply all that, when I take 1/2, okay, I'll do it like this, 1/2 times, I don't like putting fractions, but desperate circumstances, x to the fourth plus 3x squared plus 1, this is raised to the 1/2 power. When I distribute this 1/2, I'm going to have 2x to the third plus 3x all over x to the fourth plus 3x squared plus 1 to the 1/2. I should factor on x, but I don't know if I'm going to. Now I'm going to substitute in what I know. I know that my dx dt, oh, and I forgot to write that, my bad. This whole thing is dx dt, because I took the derivative of x with respect to time. So this whole thing is dx dt, which means this whole thing is dx dt times dx dt. So they're telling me dx dt is 2 centimeters per second, so that's going to be 2. And then when I do that, my dd with respect to time, I'm just going to multiply this by 2. I'm just going to put that in the numerator because it goes in the numerator. To 2, I'm going to factor out that x right in here. I wonder if that's going to mess you up. I guess you'll let me know. X squared plus 3. And just put that 2 out. Yeah, I did too much at once. And I think that's all I can do because it says find the rate of change in the distance between the origin and the moving point on the graph. So it doesn't give me an actual point. So that's as far as I can go. And that would be my final answer, is to find the formula for the change. Okay, the next one, find the rate of change in the volume of a cone if dr dt is 2 inches per minute and the height is 3 times the radius when r is equal to 6, and part B when r is equal to 24. So this is where I'm rewriting one variable in terms of another. So we did that a lot in this section. So here we go. I'm going to start by writing the volume. So volume is equal to 1/3 pi r squared h. That's the formula for the volume of a cone. Now it's telling me that the height is 3 times the radius. So the height is equal to 3 times the radius. So hopefully you agree with me that I can put that in here and eliminate a variable. So I'm going to say 1/3 pi r squared times the height, which I just said was 3r. So now when I clean that up, I'm going to take 3 times 1/3, which would be 1. So this would be pi r cubed. And that is going to be my formula. So I was given, I guess I'm going to say I was given this height was 3 times the radius. And then I'm also given that the change in r with respect to time is 2 inches per minute. So now I want to find the rate of change in the volume. So I'm trying to find my dV dt. So now I know what's going on. So here I'm going to look at this formula that I condensed. I'm going to take the derivative. Don't have to do the product roll because pi is a constant. Taking the derivative of something raised to the 3rd power, so that'll be 3 out front. There's my pi, r squared, and then since I took the derivative of r with respect to time. Now I'm going to substitute in what I know. I am looking for the dv dt, so I'm not going to substitute anything in there. For part A, I'm going to do A first. For part A, they're telling me that my radius is 6 inches. R is equal to 6 inches. And then this change in radius with respect to time is going to be 2 inches per minute. So for A, I'm going to do dv dt is equal to 3 pi r, which is 6 squared, times my dr dt, which is 2. So when I multiply all those, I am going to get 36 times 2, 72, 72 times 3, 216. I don't know if I distributed the kind or not. Pause, please. So that's going to be 216 pi, and then my units are going to be inches cubed because it's volume, and then since this was written with respect to minutes, this will also be minutes. Okay, the next one, part B, I'm still using the same formula that I came up with here. I'm still using this formula, but part B wants me to do it when the radius is 24 inches. So my change in volume with respect to time is going to equal 3 pi 24 squared times 2. And when I do all that, I get 3,456 pi inches cubed per minute. And that is my change in volume with respect to time. Okay, moving on to the next one. So now we're going to do example 5. Example 5 has an airplane that is flying at an altitude of 5 miles and passes directly over the radar antenna. When the plane is 10 miles away, the radar detects that the distance is changing at a rate of 240 miles per hour. So what is the speed of the plane? So I'm going to draw a triangle to kind of figure out what's going on. So here's my plane, and let's say it passes, this is where we might antenna down here. So right now the height is 5 miles, and that's the altitude. Then here is the distance from the antenna. So this is my distance. And right now it tells me that it's 10 miles away. And it also tells me that it's changing at a rate of 240 miles per hour. This up here will be the speed of the plane. And so the speed of the plane is what I am looking for. So what I'm going to write down, and if I force it into being a right triangle, let's call this side this A, and this B, and the hypotenuse will be C. So I'm starting with the equation of A squared plus B squared is equal to C squared. And based on this, I'm given that my A is equal to 5, my C is equal to 10, then my change in C with respect to time, because this is my C, and I know it's changing at a rate of 240 miles per hour, and I'm trying to find the change in my speed, so dv dt. So I'm going back to this equation here, and I'm going to take the derivative implicitly. So I'm going to have 3 variables. So I'm going to say 2a dA dt plus, oh, I didn't want to do that, but I did. I'm going to go down here, 2a dA dt plus 2b dB dt, taking it term by term, is equal to 2c dc dt. And then I'm going to plug in what I have. And if I wanted to divide everything by 2, I could. I don't know that I did, so I didn't. I'm not going to do that now, but you could. So now I'm going to replace, so A is equal to 5, so this will be 2 times 5, bold please, and then 2B, I got to find B, I can find B, is equal to 2C, which is 10, and then the dC dt is 240. So that's what I know so far. The dA dt, that would be the change in the altitude. And I'm hoping it's not changing because it's not, the plane's not rising and it's not falling. So that change is going to be 0. But I do need to find this B. So if I have this right triangle and I know A is 5 and C is 10, I can say 5 squared plus B squared is equal to C squared, so 10 squared. And when I do all of that, I get B equal the square root of 75. And I know I have a perfect square there that I can factor out. I'm not going to worry about that right now. So I'm going to call this the square root of 75, and then the dB dt is what I'm looking for. So since I said that the altitude is not going to change, this is going to be 0, which means this term is going to equal 0, so that's now gone. So now I'm going to have 2 times the square root of 75 dB dt is equal to, and I multiply all those together, and I get 4,800. Divide both sides by 2 times the square root of 5. And I just went ahead and found a decimal because that to me makes more sense in this situation. So I'm going to say the change to dB dt is equal to 277.36. So that, remember, is the speed of the plane. And I'm going to say the speed of the plane is 277.36 in my units for miles per hour. Okay, let's do another one. I have a conical tank with a vertex down, so it's this shape here. It's 10 feet across the top and 12 feet deep. So across the top is 10 feet, which means the radius is going to be 5 feet. And the depth is going to be 12 feet. If water is flowing into the tank, so now I'm filling up the tank, which is opposite of what that picture looks like. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water when the water is 8 feet deep. So I'm given, because just to remind you, the volume formula is volume is equal to 1/3 pi r squared h. So I'm given that my r is equal to 5. I'm given that my height is equal to 12. I'm given that the change in volume with respect to time is 10 cubic feet per minute. And I want to find the change in height. So I'm looking for find the change in height with respect to time when the height is 8 feet. So I'm going to take the derivative. Well, I have a problem because I was not given anything with the rate. So I'm going to have to somehow rewrite R in terms of H because I want to find the change in the height. So what I'm going to do is say, I'm going to change the rate in terms of the height. So when the rate is 5, when the radius is 5, the height is 12. So 12R is equal to 5 So R is equal to 5/12 H. So I'm going to substitute that in for R. So when I write this volume formula, I'm going to put this into this R. And when I do that, I'm going to have volume is equal to 1/3 pi at 5/12 squared, because that's my height, or 5/12 H squared times my height. So then I'm going to have V is equal to 1/3 pi, and this will be 25 over 144, and then this will be H cubed, when I take that H squared times H. And then when I multiply, I'm going to multiply that 1/3, so I'm going to have 25, and when I multiply 3 times 144, I get 432 pi H cubed. Now that I have that simplified, I'm going to take the derivative. This is me now taking the derivative, so dV dt, the change in volume with respect to time. I'm going to take 3 times this, so I'm going to get 75. I'm sure I can simplify, but I'm going to do that right now. H squared dH dt. That's me taking the derivative of something raised to the third power. So if I substituted what I know, and I think I really want to simplify that. 75, I'm just getting out my calculator. I'm doing 75 divided by 432. And so that change in volume with respect to time is equal to 25 over 144 pi H squared dH dt. Now I feel better, and I'm going to substitute it when I can. The change in volume with respect to time is 10. So this will be 10. There's that 25 over 144 times pi. My height, it wants me to find this when my height is 8. So my height is 8, so this is 8 squared, and I'm looking for my change in height with respect to time. So when I do all this, I have 10 is equal to, when I take this 8 squared times the 25 over 44, I get 100 ninths pi dH dt. And so now I'm going to multiply by the reciprocal. So technically I'm doing 9 over 100 pi. And when I do that, I get 9 over 10 pi, which I'm sure I want to find a decimal for. And you might have found the decimal right off the bat. Decimal is changing height with respect to time. It's going to be 0.29, if I round to 2 decimal places, and my units were feet per minute. Okay, moving on to the next one. It says air is being pumped into a balloon at a rate of 3.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So just to remind you, the volume of a sphere is 4/3 pi r cubed. And they gave me, given is that my radius is 2, and the change in volume with respect to time is 3.5 cubic feet per minute. So now when I take the derivative, I'm going to say dV with respect to time is equal to, take 3 times 4/3, and that's going to be 4 pi r squared dr dt. Oh, I forgot to say what I'm finding. I'm trying to find the change in radius with respect to time, and the radius is equal to 2. I already said that. So the GVDT is 3.5, and here's my 4 pi. My radius I just said was 2, and I'm looking for my change in rate with respect to time. So I am going to have 16 pi is equal to 3.15 in dr dt. Divide both sides by 16 pi, and I get 3.5 over 16 pi is equal to my change in radius with respect to time. And the decimal approximation for that is 0.6963. My units are feet per minute. All right, I hope this helps, and I'll see you next time in class.